class, in this video, we are going to be starting to talk about multi-electron atomic wave functions. Keep in mind that the whole reason that we introduced approximation methods, which included our variational and perturbation theories, was to think about how to actually obtain wave functions for all the atoms except for hydrogen. For hydrogen, we can perfectly solve the Schrodinger equation. However, as soon as we went to helium, remember, everything kind of went to crap, right? We had this differential equation when we plugged everything into Schrodinger's equation that was mathematically no longer solvable. Not just messy, completely not solvable. So we need somehow to use approximation methods, but how exactly do we use approximation methods and get to wave functions that we can use for any atom on the periodic table? Because before we can even think about molecules, right, we first have to think about all the other atoms bigger than hydrogen. So in this video, we're going to be thinking about that. So a common method, the most common method I would say, to determine trial atomic wave functions. So trial functions means we are using a perturbation style theory here. So we're figuring out a trial function to plug into perturbation theory, is to define our wave function. So say here it looks like we have 3 electrons, right? So this list here is our number of electrons. If we have a wave function for this list of electrons, we're going to define it as a product of single electron wave functions, where each of those single electron wave functions in this case has been called phi. So this is one way of doing it, and in fact this is a key component to Hartree-Fock computational theory, or HF. So whenever you used HF or RHF theory within WebMO during lab, this is actually what was happening. This is how the computer was approximating atomic wave functions. So this is going to be the way that we talk about. There are other ways. This is the most common and the only one that we'll talk about within this class. So how do we do that? And so how do we know exactly which trial or which single electron wave functions to use? In order to think about this, we need to go back to our conversation about quantum numbers. Remember, for the hydrogen atom, for that wave function, we learned 3 quantum numbers. They were N, which was the principal quantum number, and that had something to do with how far away the electron was from the nucleus. L, which was this angular momentum quantum number, and this told us something about what kind of orbital, what was the shape of the orbital. And then we had M, which we're now going to switch to calling M sub L, for reasons that will soon become apparent. So M, or M sub L, represented the orientation of that orbital in space, 3-dimensional space. And so we have these 3 quantum numbers, which all of our hydrogen atom wave functions depended on. However, if you think back to general chemistry, or maybe even high school chemistry, you may remember that there were 4 quantum numbers for atoms. And so the additional one, besides N, L, and M sub L, was this M sub S. Do any of you remember what M sub S was, or what it stood for? So this was your spin quantum number. So what do you remember about M sub S, or about spin? So take a second, think about that. Maybe pause the video. All right. So M sub S, or spin, technically M sub S, just like M sub L, represents a projection, except where M sub L represented a projection of where the electron was onto the x and y planes, or x and y axes. Remember, it was the projection onto the y-axis minus the projection onto the x-axis that gave us our M, or M sub L. Here we're thinking about the projection of where our electron is. The red line here, that end of that red line represents where the electron is from the origin, so that'd be our R. The projection onto the z-axis is going to give us M sub S, and so you'll notice that we have sort of 2 options. Either it can be projected onto the z-axis with a value of h bar over 2, or it can be projected in the opposite direction and have negative h bar over 2 as its projection, right? So it can either go up or down. And so we normally say that M sub S has 2 possible values, positive 1/2 or negative 1/2, spin up or spin down, right? And remember that part of this explanation for what spin was, and maybe you remember this, maybe you don't, and that's totally fine, from general chemistry, was that two electrons can only be in the same orbital, so having the same n, l, and m sub l, if they have different m sub s values. So they can have the same n, l, and m sub l as long as one is spin up and the other one is spin down. And this is known as the Pauli exclusion principle. And so in a minute, we're going to introduce a different definition of the Pauli exclusion principle. Turns out there's a few. They are completely and 100% equivalent. They just sound a little bit different, and they have sort of some different connotations that come with them. So when we think about projections, one way that we can think about this is introducing an eigenfunction. And so the way we're going to introduce spin is by using eigenfunctions alpha and beta, where alpha always returns the positive 1/2 h bar eigenvalue, and beta will return negative 1/2 times h bar. So spin up is represented by eigenfunction alpha, spin down is beta. Therefore, if we have a 1s electron that is spin up, right, so like this one, we would call that psi 100, so this would be our 1s hydrogen atom wave function times alpha. So that would be a 1s spin up electron, whereas below that we have psi 100 beta, which would be a 1s spin down electron. All right, so as promised, we have another little definition or alternative definition for the Pauli exclusion principle, and this one is quite mathematical. Right, so remember our first definition was two electrons can be in the same orbital as long as they have opposing spin, so their 4 quantum numbers can't be identical. This secondary definition is wave functions or atomic wave functions must be antisymmetric with respect to the interchange of two electrons. What in the world does that mean? There's a lot going on in this definition, so let's see if we can't tease our way through this. All right, so say we have this atomic wave function that is filled first with an electron 1, and then with an electron we're labeling 2. So we have this psi 1, 2. So the atomic wave function is first filled with electron 1, then with electron 2. And electron 1 is sitting at position R1, electron 2 is going to be sitting at position R2. Mathematically, what this means is if we change the order so that it's first filled with 2 and then filled with 1, we must negate the wave function. So psi 1, 2 is equal to negative psi of 2, 1. How do we guarantee this anti-symmetry when building a wave function? Because remember, we said that our wave function looks something like the product of many single electron wave functions that were based on our hydrogen wave functions, presumably. And order doesn't matter for multiplication, right? If we go back to math class, whenever we multiply things, order doesn't matter unless we're using operators, right? Operators acting on other operators, then order does matter. But this is what sets apart multiplication of functions or numbers from operators. All right, so how are we going to do this? So we're going to introduce one other new thing, which is called a Slater determinant. And this is going to come with a little bit of matrix math as well. So to distinguish between hydrogen-like and multiple electron wave functions, we're also going to make a change in notation. So a lowercase psi is going to represent a single electron wave function, such as that from our hydrogen solutions, and a capital psi is now going to represent a multiple electron wave function. All right, so say we want to build a trial wave function for helium, which only has 2 electrons. The very first thing we're going to do, according to Slater, is build a matrix where each element is a possible single electron wave function. We're going to base those single electron wave functions on our hydrogen wave functions because we know those solutions already. So keep in mind that we always fill from the lowest energy up. So think back to your Gen Chem days. You always started by putting electrons in a 1s orbital when you built electron configurations, and then you moved up to 2s, and then you moved up to 2p, and then you moved up to 3s, you have to fill them from the ground up, right? From the lowest energy up. And this, if you don't recall, is known as the off-bow principle. Rule number 2 here, off-bow principle. So if you didn't know that name before, now you know it's actually officially called the off-bow principle. All right, so let's build a matrix. So we have 2 electrons. We're going to have a 2 by 2 matrix. So we'll call this psi1, 2. Our first entry, which is that upper left entry in our matrix, I'll explain why this doesn't have brackets, but instead has straight lines in a little bit, is psi1s, so a 1s orbital, alpha 1. And so this is electron number 1 because, right, we have a 1 here and R1 here, right? So this is our first electron, is in a 1s orbital, and it is spin up. So that's one option. What is another option for that very first electron? Well, it could go and spin down, right? It could be in the 1s orbital, but have the opposite spin. So it could have beta spin. So there are 2 possibilities for electron 1. Notice that we put all of the electron 1 possibilities in a single row. The second electron that goes in will go in the second row with both of its possibilities, and we're going to keep it fairly consistent with the first one, in that this first column is going to be 1s spin up options. The second column is going to be 1s spin down options within our matrix. So we'll fill these in as 1s R2 alpha 2, right? Because alpha 1 alpha 2, so this is just changing the electron, but it's still 1s spin up. Either electron can occupy that spot, just not both of them at the same time. And then over here we have 1sr2 beta 2. So electron 2 spin down in the 1s orbital. So this is our matrix. The reason we have straight lines and not brackets around our matrix is because this is actually a determinant. We're going to talk a little bit more about determinants in the next video, but my challenge to you before you move on to the next video is to take out some paper and build the same determinant matrix for a lithium atom. So lithium atom, you got three electrons, so you're going to need a 3 by 3 matrix. So try and follow the same pattern and build the Slater determinant matrix for a lithium atom. See you soon!